Hello, Mr. Sorrentino here again, and I'm doing yet another one of my videos for the Math 31 course. And this video deals with the last section of Chapter 5, which is 5.6, Applications and Models, Growth and Decay, and Compound Interest. Basically, in this section here, you're going to be reacquainted with a couple formulas. You were taught these two are formulas that you can use for exponential growth or decay. And it really depends on the situation that you are asked to encounter. I provide both of these. The book kind of focuses on this one a lot, and the reason being is that it's the one that's most often used in calculus. The difficulty with it is that the way that the textbook has you address this one is a little sketchy. And that's because what they define this to be as it is the exponential growth rate and instantaneous growth rate. But basically, if a textbook says like you have bacteria growing at a rate of 5% per hour, say. Now, as long as you let your t be in terms of hours, you're good. And they would say that would allow you to say that k is 0.05. And of course, if they eventually say decaying, if they said decaying, k would equal a negative 0.05. And although the answers, are not going to be extremely far off, if you're talking about having numbers in thousands, you might be off by as much as 10, because exponentials, whenever you have a slight differences in values that you're putting into them, you can be off quite a bit. Then, as a result, you could end up having, an answer that, if, you didn't interpret it correctly, that could be off as far as the math lab, your homework goes. I usually recommend doing this for the percentage, problems where they just say per year. But sometimes you're going to have situations where it says percent per maybe 3 years. They'll say like it grows 5% every 3 years, and then then you have to do more of the setup that I'm going to show anyway. This one's a little easier to do because A is basically your growth or decay. This kind of goes along with most of what we've done in this particular unit because, we had a growth. Remember, our A was greater than 1, so you're talking about numbers that are over 1. If I said like if I had 5% growth, that's 1.05. And if I said 5% decay, that would be 0.95 because basically this means that 100% plus 5%. This means 100% minus 5%. That's what the decay is. So, it's something, but the issue with working with that is making sure you pick the right value for this. Whereas this one here, you're going to see discrepancies between how it should be done versus how they're having you address it, which is basically a shortcut. And it's a shortcut that gives you a good approximate value, but if you want to be more exact, you should really do the two-part process I'm going to eventually be showing. And I'm going to kind of go into that a bit. When we head down into the compound interest formulas, you have two formulas. The one in 5.2 is the one we're most often used to working with. And so if you have words written like, annually, semi-annually, quarterly, monthly, and these would be the primary ones that you'll see. There was others that we mentioned like daily, hourly, and things like that. But you're not going to probably see most of those. These are the main four you're probably going to see. This is the one you use. This is, the regular compound interest formula. Now, if it says compounded continuously, which basically means you're taking the interest rate, splitting it up into infinitely small parts and applying it an infinite amount of times. This is the one that you would use. There's not many like bank accounts that compound continuously, but there are things that in biological systems that have continuous growth rates. So, and basically it compounded continuously kind of gives you the maximum effect of compounding. So basically, if I said, okay, what's the most I could get off of this account at 5.9% interest? It would depend on how much it's compounded, but if you want to get the maximum possible value, you would compound it continuously. Where these are still standing for the same things. R is still the interest rate written as a decimal. If you have like 5.9%, have to convert that to 0.059. A is the amount after t years, or we sometimes would call that the accumulated amount. And P is the initial amount, which we would often call the principal. So that's going to be a new one's going to be added to the list of things that we were looking to do as well. So let's get to the first example, which actually does deal with compound interest. Now, one of the things that's also different in this particular chapter is when we go back to 5.2, most of all the questions you were asked were, written to find the amount that's accumulated, and that's about it. In this particular section, you could be asked a lot for the time it takes for something to happen, as well as, what would the principal need to be in order to get accumulated amount of this much, in this amount of time with this much interest and so forth and so on. So, and that's because now we learned how to handle logarithms and deal with exponential functions in that way, and we could actually solve such equations. Because if you look at this here, you have an initial amount of $10,000 is invested in a certificate of deposit, CD, with 5.9% annual interest rate. So right now what I would have here is I have A, as far as the information that's given outright, I have A equals $10,000, which is the principal, times 1 plus 5.9%, as shown already, is 0.059, over, now we haven't been told that it compounded, the number of times compounded yet, because that's coming in the next parts of the question, and I have n times t. So there's information here that I'm still looking for. And now as you look at the first two questions, it's asked how long will it take for the investment to double if the interest is compounded monthly? And how long will it take for the investment to double if the interest is compounded continuously? So you can see here we're looking for t. It's always important to know what variable in this formula we're looking to find, because that means that the other information, either directly or indirectly, needs to be given. And that information is given. I mean, as far as n goes in both of these, here n equals 12. So, I have that part of the formula. And here, compounded continuously, I know that I wouldn't be using this formula. I'd be using this one. So I have, that information here. Now, again, I'm still looking for t in both of these cases, and right now I have two variables. I have t and I have a that's not known. But here's where I know how to figure out what a is. I want the investment to double. I want the accumulated amount to be twice what I started with. So that doubling tells me in both these cases that A is going to equal 20,000. With this now, I could now answer these questions, because now I can say, okay, well, here I have 20,000 equaling 10,000 times 1 plus 0.059 over 12 to the 12t power. And so I want to start solving this and simplifying along the way. I'm going to divide both sides by 10,000. That's going to give me a 2. And I'm going to simplify this inside here. 1 plus 0.059 divided by 12 is 1.004916 repeating. Now when I deal with problems like this, I make sure that I keep the full amount on my calculator. I'm not going to start rounding here. I'm going to make sure that either by using the previous answer command, which is hitting second and the negative button on a TI calculator, or using the memory feature, which basically using the store feature, you can store the number in for any variable and make use of that. You can actually keep the number as accurate as possible, because even if the calculator is showing you about 8, 9, 10 decimal places. It has many, many more stored in its memory and how it was calculated. So it's going to give you the most accurate answer if you can keep it to completion. To make more room for this part of the problem, I'm going to scooch over here, kind of start with that formula there. So I have my 2 equaling 1.004916 repeating to the 12t power. I want to solve this equation. I can rewrite this as a logarithmic equation. However, if I'm writing it as a logarithmic equation, I'm going to have a base 1.004916 repeating. That gets kind of sloppy to write. And also, along with that, I'm probably going to need to use a change of base formula anyway. So what I'm going to end up doing here is I'm just going to say, okay, I'm just going to apply a logarithm on both sides. Because what that will do is that I'm going to have the log of 2 on this side, and I'll write it as I would put it in the calculator. Realizing that's just going to be a number, I'm going to have, well, since I have a logarithm here now, this 12t can be brought in front. So 12t times the log of 1.004916 repeating. I want to solve this equation. Out of this, I can actually factor out a t and say t times 12 times the log of 1.004916 repeating. Recognizing now that this is just going to be a number, all of this is just going to be a number. So I basically have a number equaling t times some other number. So obviously to solve for t, I'm going to divide both sides by that 12 times the log of 1.004916 repeating. So I would have this. And again, on the final exam, you might be asked to provide the logarithmic form of the answer that you would plug into your calculator to get the final result. And that's what this would be. So now if I put that in my calculator, I'm going to get t equals 11.78 years. And actually, I should technically be a wavy equal sign because it's approximately equal to. So, that's the answer I get for this one. Now, compounded continuously. Compounded monthly, if you remember when we were talking about that, once I'm up to this point here, there's not much of a difference between monthly to daily, to hourly, and things like that. So I'm not expecting a huge difference between having it compounded monthly versus compounded continuously. I would expect the answer for part B to be maybe slightly shorter than 11.78 years, but it's not going to be probably significantly so. And again, I'm just going to use the information that I have, and since because of the doubling, I now know again that that's going to be 20,000, I should say, equaling 10,000 e to the 0.059t. I would divide again both sides by 10,000, and I would get 2 equals e to the 0.0059t. One of the good things about using situations where there's e involved, you don't have to sit there and worry about logarithms and the change of base, because there's only one logarithm you would use, natural log. So to move further into this question, I would say that the equivalent logarithmic statement would be that 0.059t would equal the natural log of 2, and t would equal the natural log of 2 over 0.059. And when you work that out, you get about 11.75 years. So again, as I said, not a major difference, but it is slightly shorter. For part C, we want to figure out an annual growth rate for both of these situations. So I'm going to have a situation that represents A again, and one that represents B again as I do this work. Basically what this is asking you to do is figure out what is the percentage growth in a year's time based off of the fact that we do have a 5.9% annual interest rate, but with the compounding, I'm going to actually be adding more than 5.9% to my initial investment in a year's time. I want to figure out what that percentage actually is. And so what I need to do is figure out basically a final amount minus the original amount. I want to divide that by the original amount and multiply that by 100%. And that's going to be the same in both cases. I'm going to take the final amount, or the accumulated amount, subtract away the principal, and then divide by the principal and times 100%. Now, that 100 times 100%, when we use that, oftentimes in math, that means that we're going to be, multiplying the result by 100, so we can present it as a percentage rather than as in decimal form. So getting back to A, since it's an annual growth rate, I know that T equals 1. That's going to be true for both of these situations. And so I want to see what the accumulated amount is when I have 10,000 with that 0.059% interest rate, compounded monthly. And technically I put times 1 out here, but 12 times 1 is just 12. So I'm just going to keep that. And so the final amount for this ends up being approximately $10,606.22. And since we're dealing with money here, it's okay to kind of round off the decimal places. Technically, you really should kind of keep the exact account in here until you calculate what the percentage is. But my annual growth rate now is going to equal, well, if I take this amount and subtract away 10,000, I'm just going to have $606.22 over that 10,000 times 100%. And that equals about 6.0622%. So not significantly more than 5.9%, but it's still more than 5.9%. Whereas for B, I'm going to do the same thing, except now I'm going to use the formula. A equals 10,000 e to the 0.059 times t, which would be 1. So A is approximately going to be equal to $10,607.75, which means when I use the formula and do my annual growth rate, I'm just going to say AGR for this, equals, it's going to be that 10,607.75 minus the principal of 10,000 is going to give me 607.75 over that original 10,000 times 100% is going to equal 6.0775%. So again, between these two, the annual growth rate is about 6.08%, whereas the other one was 6.06%. Not a huge percentage difference. For example 2, we're going to kind of look at the two different types of formulas we have for any other type of growth or decay and see what the difference between them is. Now, know some of the terminology, and be aware that the shortcut that the textbook does provide will give you approximately a somewhat good enough value in many cases, but it's not going to be as exact as other methods. So I'm going to show that as well. So let's have a look at example 2. Now, I was looking at example 2 here. Keep in mind that a lot of the problems that you're going to be given are going to say like 5% per year, 5% per day, 5% per month, whatever. Whereas this is saying 5% every 8 years. When you start having situations like this where it's not per year, per month, per day, it's not a percentage per one single unit of whatever it is, you're going to have to use a two-system setup, or I should say two-step setup, which means it's going to take you 2 steps to get the problem done right, because in step 1, you're going to find, depending on which formula you're using, either A, if you're using the formula you suggested in A here, or you need to find what K is if you are finding, if you're using the second formula that's indicated in B. And then this will lead you to having a formula with enough information in it, and then that lets you go to 2 where you can actually answer the question. In both these cases, I had to set up the equation a certain way, or the formula a certain way, solve it, get what I need to get the formula, and then I'll have the work with that. So in part A, they say find the formula of the function that describes the situation in A equals P A to the T format. So this is an instance where we're going to need to find out what A is. Now, if this had said 5% every year, if it had said that instead, like 5% per year, then A would have that would have been really simple. A would be 1.05. That works out really nicely. However, again, you have to remember that this isn't the way that it tends to work out very well, and with this, because now it's 5% every 8 years. So I actually have to go through a process to figure out what A is if I'm given this kind of situation. And so for this one here, I had to actually set this up and say, okay, well, I'm going to first start off with knowing what I know here. A equals P A to the T. And basically what I'm told is that in 8 years' time, my final amount, given this initial value P, now I could put a number in there, any number I pick, and since we're doing percentages, it'd be 100. But it stands to reason that if I start with this amount P, then A would be 105% of that initial amount. And then when I go through the solution process for this, I could say, okay, well, the first thing I would do is divide both sides by P, because I'm trying to figure out what A is, and I would end up with A to the 8th equals 1.05, and then A would be the 8th root of 1.05. Now, for purposes of writing formulas and stuff here, I'm going to evaluate what that is. That's 1.0061117. Good enough. And so my formula ultimately for this is going to be A equals P 1.006117 to the T power. When I do the same thing for B, I'm going to start with this A equals E to the KT. I don't know what K is. I do know, again, and that's PE to the KT. I do know that after 8 years, with an initial amount of P, again, I'm going to have 105% of P for my accumulated amount. And so what I basically have at this point, when I divide both sides by P again, is that I have E to the 8K equaling 1.05. And so to solve this for K, 8K is going to be the natural log of 1.05, which means that K is going to be the natural log of 1.05 divided by 8, which is, again, for formula purposes, is approximately equal to 0.006098. And so the formula that I would use if I'm using this one is A equals P E to the 0.006098 T. Now here's the difference between an exponential growth rate and an annual growth rate. First of all, in many cases, your textbook treats them as being the same thing. So if it says 5% per year, for instance, they'll say that that's the same thing as the exponential growth rate. The exponential growth rate is K. And as we see here, that's 0.006098. And if I wanted to write that as a percentage, that would be 0.6098%. So that's how much your investment or this population is growing over a period of time. It's not actually per year. It's basically, it's kind of hard to explain what the exponential growth rate is. It's not really an annual growth rate. The annual growth rate comes from actually A. The A equals 1.006117, which, if I wrote it as a percentage, is 100.6117%. Well, that's an amount that it's kind of telling me what the growth rate is, because this is the growth. I mean, anything over 100 is how much it grew. So the annual growth rate is actually 0.6117%. As I said, though, word of warning, your textbook treats these the same. They aren't. They really are not the same. So as a result, especially when we start dealing with situations where you're talking about bigger values, you have like an initial amount of like 1 million, and you're looking for amounts or times and things like that. This percentage difference, I mean, if I round both of these off to two decimal places, it's 0.61. I mean, yeah, the K is a good approximation of the annual growth rate, but it really isn't the same thing. Now with both of these, I can figure out what the doubling time is. So as I work on this doubling time as well, I'm going to be showing you how to do this using either of the equations. Because in both cases, I've already found out a good formula to use. I have this one, if I'm using the formula, or the A equals P times A to the T format. And so I could say, well, I could use A equals P times 1.006117 to the T power. Or I could use the one that we just got from part B, which would be A equals P e to the 0.006098 t. In both these cases, it doesn't matter which one I make use of, and you're going to see this as we do the calculations. Now, I'm looking for a doubling time, and that means that I'm looking for, I want to find t when my final amount is equal to 2 times my original amount. So I'm just going to let A equal 2p for this one. Now a couple things happen here. The p's we cancel out, because the first thing I would do is divide both sides by p. I can't turn an exponential equation into a logarithmic one if I have anything being multiplied to the base. And all it's going to do is cause the p's to cancel here. And the reason why, again, I'm using p's is because I didn't define what the starting value was. I'm just going to apply a logarithm to both sides of this, because now I'm going to have t times the logarithm of 1.006117 equaling the log of 2. And this is log base 10 because I'm not putting a base down there. And so t is going to equal the log of 2 over the log of 1.006117, and that's going to approximately be equal to 113.7 years. I could do the same thing with this formula over here. Again, my final amount would be 2 times my original amount. I would divide both sides by whatever that original amount was, because again, even with the base e, I cannot turn it into a logarithmic equation until I just have the exponential and the base and its exponent. The other thing that's going to be different here is, since e, this is I mean, all I have is the base e, it's probably just best to use a natural log. So I'm going to have 0.006098t equaling the natural log of 2, which means t is going to be the natural log of 2 over the 0.006098, and you would find out that that's approximately equal also to 113.7 years. So it doesn't matter which formula you utilize for this. It's just you need to make sure that you keep it straight and you've already set it up. You've either found out what the base A is if you're using the one outlined in A, or you've found out what K is in the instances where you're using PE to the KT. So let's get in and do another example. Now I'm not going to do it both ways. I'm just going to show you an example 3. We're asked to do it using the PE to the KT. So let's have a look at that. So we have this problem here. An unknown substance is decays at a rate of 10% every 3 days. What is the half-life of the substance? Now again, you're not being told here what the original amount of the substance is. And again, it really doesn't matter. I mean, it's losing 10% every 3 days. So if I had 100 pounds after 3 days, it'd be 90 pounds. If I had 10 pounds after 3 days, I'd have 9 pounds. I'm losing 10% each time. So it doesn't matter, what values I use. So now the thing is, again, one of the things you sometimes run into is that students will think that, since I'm using this A equals PE K to the T power, they want to say, well, K is going to be, equal to -10 or -0.10 because that's 10% over 3, which is a -0.03 repeating. And some of the things that the textbook is leading on with would make you believe that is true. And the thing is, they're using a rule that only works as long as you're dealing with very small percentages. And very small percentages, you're talking about usually 5% or less. And they're applying it to a situation where, you have percentages that, are, sometimes more than 5%. So you have to be careful with things of this nature because the textbook is using something that is a good approximation as long as you have a small percentage growth or decay. If you get over a certain percentage, the discrepancy between using K, estimating K in a manner like this, and how to actually go about doing it is going to start causing a much bigger difference, especially when we're dealing with, percentages and large amounts in some cases. So I'm going to use a two-step process. I have this formula I want to use. My first one is I'm going to find K. I'm going to expect it's going to be somewhere close to this. And by the way, that's -0.333 or 0.333 repeating. But I'm going to expect it's going to be close to that, but it's probably going to be off ever so slightly. So let's have a look at this. I'm starting with an original amount. I don't know what it is. I don't know what K is yet. But after 3 days, I'm going to have 10% less. Now, the thing else to remember about these formulas, especially for decay problems, if I'm decaying at 10% every 3 days, that means after 3 days, I'm going to have 90% left. These formulas always deal with the amount present, not the amount lost. And so the final amount is going to be 0.9 or 90% of P. Now, of course, as I go through to carry through the solution process to figure out what K is, this would cancel. I would have now that 3K would equal the natural log of 0.9, which means K would be the natural log of 0.9 over 3. And if you work that out, you get it to be approximately -0.03512. So as you see, close to what this was up here, although it's written sloppily. I'll write it a little bit better. Although close, not exact, and sometimes that difference can cause some major discrepancies when you answer questions like this. When you're looking for times, it's usually not going to make a big deal, but if you're looking for amounts, that's going to cause a bigger situation. It's going to cause a bigger issue. So now we're actually able to do part 2, and we're going to answer the question. Because we now have a formula. We now have the complete formula, A equals P E to the -0.03512 T power. We want to figure out what the half-life of the substance is. The half-life, if you ever taken a science course or read through the textbook, because they define what a half-life is as well. A half-life is the amount of time. So this is asking us to solve for T. It's the amount of time it takes there to be half the original amount. The original amount being P here. So for me to solve this, I'm going to have to let A be 1/2 of what P was, half the original amount. Divide both sides by the original amount, you would get 1/2 equals E to the negative 0.03512t. And I would natural log both sides, so I would have that negative 0.03512t is going to be the natural log of 1/2, which means t is going to be the natural log of 1/2 divided by negative 0.03512, and that's going to be approximately equal to 19.74 days. And so every 19.74 days, this amount of substance, it becomes half the amount it was. Logistic growth, they talk about in the textbook. I mean, you may see a question come at you regarding it, because it's really not going to ask you to do a whole lot. It's not going to. It's going to ask you to do some plug and chug. It's going to ask you to do some things where you may have to manipulate the overall equation and solve for something. So we're going to see some examples of this. So when we look at this one here, and logistic growth is basically, as it's explained, is a growth that realizes that, in biological systems, I could have something start off with an exponential type growth. However, usually since the amount of space is not increasing, if there's a forest, and the forest, as long as it's not being cut down or anything, if it's left alone, it's going to stay the same size. If I have a population of deer in it and they're growing, well, sooner or later, if they're left to keep growing, eventually what's going to happen is that there's not going to be enough food in that forest to feed them all, so they're going to start dying off, and it's going to start stabilizing how many can actually be kept in there. So that's more of a logistic growth, where it kind of says, okay, well, we start off having an exponential, but it kind of veers off after that. And they often have this format where you have some kind of constant number over, some expression involving, and most of the time it's going to be e to a power, but sometimes they will have another base here. And notice that is a negative exponent up here overall. It's a negative 0.5, or oftentimes it's going to be a negative number times t. You want to keep that in mind, because some of the things that are going on here, you want to be aware of about how to handle this. So for instance, we have this function p of t, which equals 3200 over 1 plus 5.40 e to the negative 0.5 t, where t is the number of months after it is stocked. And so they're saying, okay, based off of this logistic function, how many fish were initially in the lake? It's just we're not being told that. Well, that means, from our function usage before, that means we're essentially looking for p when the time is 0. So that's going to be 3200 over 1 plus 5.4. You really don't need to put the 0 there for my writing purposes. This 0. Since we're talking about the number of fish in a lake, I'm going to probably want to approximate it better by rounding it off. Mostly because of the fact that, what does it mean to have 0.8 of a fish? Does that mean a fish and its tail cut off, or what does that? Doesn't really make any sense. So, just how many fish approximately are in there, it might be better to round it to the nearest whole fish. But what's nice about this is, it's pretty easy to do. Since I have an exponential function here, this becomes 0. Anything to the 0 power is 1. So this is basically, all of this over here is basically 1. So I basically have 3200 over 1 plus 5.4, which is 3200 over 6.4, which is equal to 500 fish. So there were 500 fish initially in the lake when it was stocked. They stocked it with 500 fish. What is the maximum number of fish that the lake can sustain? Now this one's a little bit problematic, because what I want to do is figure out what p of t is And you'll start using other notation for this as you get into a little bit of pre-calculus and especially in calculus. As t approaches an infinite amount, as we keep going and going and going and going, assuming that we're not going to stalk it again, which isn't really what happens typically. But if we kept going and going and going, what's the maximum number of fish that the lake can sustain based off of what this function's telling us? Because this function would eventually level off at a value, at a y value where I'm not going to go past that. It basically does have a horizontal asymptote, and I want to figure out where that is. So I had to think a little bit about this. I was going to say it's the maximum p of t would be, well, I'm going to have the 3200 over 1 plus 5.4 e. Well, let's think about what goes on with this. Let's not even go with that exponential there. And this is what they want you to do with this, to think about what's going on here. If I have, it's a side note here, e to the negative 0.5 t, and I put a value in there. If we put the 0 in there, that's 1. If I put 2 in there, I get smaller. I put 3 in there, I get smaller, because this is basically reciprocating. This is basically saying I have 1 over e to the 0.5 t power. Now, if t keeps increasing, this denominator keeps increasing in value, but the top doesn't. The top remains 1. So if I have a 1 on top and I have a number that keeps getting bigger and bigger and bigger on the bottom, what is the value of this fraction going to approach as t keeps getting bigger and bigger? That basically becomes 0. So this exponential thing, when I have t approaching infinity, is just going to become a 0. And that means that it's going to, in this case here, I'm going to have 3200 over 1 plus 0, which is 3200 over 1, which is 3200. Please, please, please do not assume that the number up here is always going to be the maximum number of whatever they're talking about. This function down here doesn't have to have a 1 in this position. So keep that in mind. The other thing you have to remember is if I'm looking for the maximum number, that means t is going to infinity, and the exponential portion will be approaching 0. So that's what I want to, I want to take the exponential portion and replace it with a 0. So 5.4 times 0 would be 0, and 1 plus that would be 1. So it works out in that way. Now, as far as, the question in C is asking, it's asking essentially, okay, what's P of 11? So this one here is just more of a plugging it into your calculator correctly, making sure you use your parentheses correctly and everything. And so if you do that correctly, you would get about 31 fish, rounding it off. And now it says, how long will it take for the population of fish to reach 1,000? So now we're saying, okay, we know that P of t equals 1,000. And of course that equals 3,200 over 1 plus 5.4 e to the negative 0.5 t. I want to solve this equation for t because it's asking for us for how long, so it's kind of an indicator that t is what we're looking for here. And I want to also keep in mind that, I have a fraction on, basically something written as a fraction on the right. I can rewrite this as a fraction, and I can cross multiply. So I'm going to have 1,000 times 1 plus 5.4 e to the negative 0.5 t equals 3,200. When I distribute the 1,000, I'm going to have 1,000 plus 5,400 e to the negative 0.5 t equaling 3,200. I would subtract 1,000 from both sides. I would divide both sides by 5,400, and it would basically reduce to a fraction of 11 over 27 when I simplify the fraction completely. I need to get rid of the exponential base e, so I'm going to turn this into a logarithmic equation. So negative 0.5t equals the natural log of 11 over 27. And t is going to be the natural log of 11 over 27 divided by negative 0.5. And when you calculate that out, it's about equal to about 1.8 months. And that brings us to the end of this video. If you have any further questions, please make sure to bring them up in class or see me during my office hours. Until I see you at one of those places or until the next video, have a good day. Bye, everybody.